Now we give the proof of the undetermined coefficients method. So we solve the non-homogeneous linear differential equation Ly equal to G. Here L is a linear differential operator which constant coefficients. The coefficients of the ith derivative of y is ai. So the notation is slightly different from our previous notation. Previously, for linear differential operator with constant coefficient, we use Ly equals sigma Pn minus kyk. The case ordered derivative, the coefficient of the case ordered derivative is Pn minus k. Now we use ak. This is not essentially different. This is for the simplicity of notation later. And so our equation is Ly equal to G. Now G is an nth ordered polynomial. Okay. So since we are considering nth ordered operator or nth ordered equation, therefore the coefficients of the nth ordered derivative of y, that is an, we assume that an is not 0 here. Okay. So the theorem for this simpler case is that if 0 is not a root of the characteristic equation, that is this polynomial e lambda, then we can choose suitable bi, capital B, such that this nth ordered polynomial y, which is coefficients capital Bi, is a solution of our non-homogeneous equation. This Ly equal to the polynomial with coefficient small bi. That is our equation 2 here. Okay, this is the starting point to prove the method of undetermined coefficients. So to prove this theorem, we need to develop some computational skill. So firstly, we will use the sigma summation symbol. As we all know, the sigma xi is x1 plus maybe x0, because my I here is from 0 to n. If I from 1 to n, then it is xi plus xn. Okay, so the I here simply is a dump index summation variable. Obviously, if you change the I denoted by j, using another letter to denote the summation index or summation variable, the sum will not change. Both sides of this equality means x0 plus x1 plus xn. Okay, so they are equal. And sometimes we need to study double summation. That is the summation number, the sum of the number has more than 2 index, or at least 2 index. For example, here is sigma ai j, sigma. Firstly, we sum the index j from 1 to n, and then we sum the index I from 1 to n. Okay, so a very useful property for double summation is that they can switch freely. This equality holds for complex numbers aij. Okay, so the left hand side means firstly we sum the index j from 1 to n and then I from 1 to n. And the right hand side means that we sum the index I first from 1 to n and then j from 1 to m. But the result is the same. This result is quite obvious, but if you want a proof, we can arrange our aij into a matrix. The left upper corner of this is the matrix aij. Then we sum the rows to sum the first row, we get a1j. Sum the second row and the nth row, we get anj, the sum of anj. Well, if we sum the column wise, the sum of the first column is ai1, I from 1 to n, and the sum of the mth column is ain, I still from 1 to n. So then the left hand side of our this equality we want to prove is precisely sum the aij row wise to get the sigma a1j, a2j, sigma anj, and then sum the result together. Okay, well, the right hand side of our equality for is we sum the numbers column-wise first, and then sum the result. Obviously, both sides of 4 means all the numbers in this matrix, the sum of the number in this matrix Aij, therefore they are equal. Okay. So sometimes we will study double sum in this manner, where the inner sum, the range of the inner sum depend on the index of outer sum. Here the index of inner sum is j. J is from I to m, but I is the index of the outer sum. So this double sum is quite different from what we prove in this theorem, this lemma. Here the range of inner sum and double sum, the range of the inner sum is fixed. For example, the left hand side fixed from 1 to m, does not depend on the index I. So this is different. This kind of double sum is somewhat different from from this sum. Okay, because in this double sum, the range of the inner sum depends on the index of outer sum I. Okay, so to deal with such a double sum, we introduce a number delta ij, which means if j is less than I, the result is 0, and j is greater or equal to I, the result is 1. So then using this sum, for example, this double sum that is here can be written as what? The inner sum is j from I to m, but we can write it from 0 to m. But for j less than I, those sum we consider the 0. Therefore, we introduce a factor delta ij. Then if j is less than I, the term is 0. Therefore, you sum from j from 0 to m is the same as sum from j from I to m, because for j less than I, the terms are 0. Okay, so this equality is obviously true. Then having transformed this sum into this new sum, which the delta ij introduced, the range of inner index does not depend on the outer summation index I anymore. Therefore, we can switch the order of the sum using the lemma we just proved. So we switch. So we get this result. But for this result, we consider the inner sum. If j less than I, that is if I greater than j. If I greater than j, then the delta ij is 0. Therefore, the sum from I from 0 to m is actually from 0 to j. Because if I greater than j, the term is 0. The terms are 0. So we have this equality. Okay, so this equality is not obvious, but with our trick introducing this delta ij, it is easily proved. Okay, so having this preparation, we can prove our theorem. That is the starting point of our undetermined coefficient method. Okay, so firstly, our equation is this equation. The right hand side g is an mth ordered polynomial, but we don't know whether whether n is greater than m or not. N and m, we don't know which one is the largest one. So we can assume that always assume that m is not less than n. Because if m is less than n, we can let the coefficient b to be 0. Therefore, the sum from I from 0 to m is actually from 0 to n. Okay. For this reason, we can assume that m is not less than n. So we always assume m larger or greater or equal to n. Okay. So then we compute the derivative of y given in this equality, because we want to prove that we can choose some coefficient bi, so that the polynomial which coefficient bi is a solution of our equation. So we compute the derivative of the y given by this equality, the derivative of this. So the first derivative is bj and j, because the y is bj tj. So derivative is bj j t j minus 1. Okay, so this is the first derivative of y. And the second derivative, so you take derivative again, you get bj j minus 1 t to the j minus 2, and so on. In general, once I is less than m, once I is not greater than m, the derivative yi is given by j from I to m, and is this result. This is why we assume that m is not less than. This is the reason why we assume m greater than or equal to n, because we will take derivative up to order n. So if m is less than n, the computation will be quite different. But if m is greater than or equal to n, then this formula is always true for I from 1 to n. Okay, and the coefficient has many terms. We can use can be expressed by this by this fraction to denote the multiplication of j minus 1, j minus I plus 1. Okay, so this is a very simple expression for the ith order derivative of y. Here I is 0, 1, 2 until n. I is up to order n. This formula is true. Therefore, we substituting this derivative into Ly into our differential operator. Then our Ly is sigma ai y ith order derivative of y. And using the previous formula, we get I from 0 to n ai, then j from I to m, j from I to m, bj, and this is just the previous yi we compute here. Okay, then we use the previous trick, this trick to switch the summation order. Okay, so using this trick, this sum I from 0 to n, j from I to m, I from 0 to n, j from I to m is equal to j from 0 to m, I from 0 to j. Okay, so using this result, this sum could be written in this way. Here the ai, because ai does not depend on the inside summation j, so we already moved ai into the summation. Before switch the order of ij, we move ai into the summation, then switch the order, so we obtain this equality. Now we set j minus I to be k, so this sum can be written in another form. Okay, j minus I is k, so this is a j minus k. Let's have a look. Tk, t to the power k, and the range. So I from 0 to j, so k also from 0 to j, so this is equal. Both sides, this equality is true, because the range of I and k are the same. I from 0 to k to j, then k is j minus I, so j is also from 0 to j. So this sum we will switch the orders again. To switch the order, we introduce a delta kj. Delta kj, that is if k greater than j, delta kj is 0. So we introduce the delta kj so that we can change the range of the inner sum for the k from 0 to j by k from 0 to m. This is the we introduce this delta kj so that the inner sum, the range of the inner sum, does not depend on the outer sum index j, so that we can switch the order. Okay, so we move this, we switch the order of this double sum. Switch the order. Here we first the k and then j. Now we first the j and then k. So we get this result. For this result, we will get rid of the delta kj. Therefore, to remove the delta kj, because if j is less than k, the terms are 0. Therefore, the result is actually j from k to m. Okay, so we get this result. This result, the inner summation is with respect to j, but the tk is does not depend on the inner summation variable. Therefore, we can move the tk outside the inner summation. So we get this result. What's this? This is ly. So ly is a polynomial of order m also, and the coefficient of tk is this summation for j. Okay, compare this with ly equal to g. So g is a polynomial of order n, and in the polynomial g, the coefficient of tk is small bk. So comparing the coefficient of ly and g, we see that this number, inner summation, should equal the small bk. That is the coefficient of t to the power k in the polynomial g. So we got this equality. Okay. So we set to simplify the notation, we set this number to be alpha ij, and so this equation for k equal to 0, k equal to 0 means j from 0 to m. So this is alpha 0 0 b0 plus and until j equal m. Therefore that is what's this? This is for k equal to 0. In this equality, k take 0 and j from 0 to m. Therefore we get this this equality. Okay, this equality is the case for the equality 8 for k equal to 0. When k equal to 0, this is alpha ij, and the range of j is from 0 to m. So we get this result. And then for k equal to 1, the range of j is from 1 to m. So we get this result. And so on until j equal to m. When j equal to m, we simply have alpha bm equals bm. Okay, so we got this. We consider this as a system of linear equations for b0, capital B0, capital B1, capital Bm, and we want to. It's sufficient to ensure that this system of equation has a solution. But this is true because a0 is not 0. What's a0? a0 is the coefficient of Yes, a0 is not 0. Why? Because if a0 is the 0 order term of the characteristic equation, characteristic polynomial, a0 is the constant term of e lambda, because we assume 0 is not a root of e lambda. Therefore, this implies that a0 is not 0. Okay, so from a0 is not 0, we see that all the alpha ii is not 0. Therefore, we can solve this system to obtain capital B, B0, B, capital B1, capital Bm, so that the equality 8 is true. Equality A is equivalent to Ly equal to G, because the right hand side of equality 7 is our capital Ly, is the linear operator applying to our y, and G is the polynomial which is coefficient small bk. So this equality 8 means that Ly equal capital G. Both Ly and G are polynomial of order m, and this equality A means that the coefficient of tk are the same. So this means that using the solution capital B0, capital B1, capital Bm for these systems of equation, the coefficient capital Bj will satisfy this. Therefore, the corresponding y will be a solution of this equation. Okay, so this proves the simplest case, basic case that 0 is not a root of the characteristic equation. and the right hand side is purely polynomial. Okay. Of course, we have other case. 0 is a root, and also some exponential function. We will delve into this later. So now the general case is that Ly is G. So G is satisfies the following cases. First, G is a polynomial, as before. G is a polynomial. But in our previous theorem, we assume that t equal to 0. We assume that 0 is not a root of the characteristic equation. We assume this assumption. 0 is not a root. Okay. Now for the general case, 0 might be a root of some times. Okay. So let's see what happened. So if 0 is not a root, not an eigenvalue, that is 0 is not a root of the characteristic equation, then this non-homogeneous ODE has a solution of this form. This is precisely the theorem we just proved. And if 0 is a root of the characteristic equation of times k, then the solution would be the polynomial multiplied by the tk. So this is a new case. We will delve with it here. Okay. And also, if our gt is a polynomial multiplied by an exponential function, and this lambda 0 is an eigenvalue of the characteristic equation of times k. Of course, if k is 0, then this means lambda 0 is not an eigenvalue of the characteristic equation. Lambda 0 is not a root of the characteristic equation. So this k might be 0. Okay. In this case, our solution is t to the power k multiplied the polynomial, nth order the polynomial, but the coefficient capital Bm, capital P0 will be determined by substituting this y into the equation and comparing the coefficients. And also we need to multiply exponential lambda 0 t. Okay, this is the second case. The third case, the undetermined coefficient method could deal with is involving the sine and the cosine. That is, if gt is an mth ordered polynomial multiplied cosine beta t plus another polynomial of order at most m multiplied sine beta t and then exponential alpha t. Then we have alpha and beta, and then we can construct a complex number. Lambda 0 is alpha plus or minus I beta. So if this lambda 0 is an root of the characteristic equation of times k, then the solution would be tk, another mth ordered polynomial cosine beta t plus qmt. This is also mth ordered polynomial sine beta t and then exponential alpha t. Okay, so these three cases are the form of gt, so that the method of undetermined coefficient could apply. Okay, so here the small pq and the capital PQ are polynomials. Okay, so to prove this conclusion, firstly, as I said before, the case one is that gt is a polynomial and 0 is not an eigenvalue. Okay, this is the result of the theorem we just proved. Okay, so the other case B means g is a polynomial, and this case is g is still a polynomial, but 0 is now a root of the characteristic equation of times k. So this is the case 1, sub case B. So for this case, because 0 is is a root of the characteristic equation of times k. This means that the coefficient of the polynomial equation, this E lambda, the a0 until ak minus 1 will be 0. This is equivalent to the assertion that 0 is a root of this characteristic equation of times k. Okay, as you can see. So we have ak minus 1 and ak minus 2 and a0 are 0. Therefore, our equation becomes this equation. Start from the case ordered derivative of y. We have no lower order term anymore. Yk minus 1 and y itself are missing from the equation. So for this equation, we can introduce a new dependent variable z to be the case ordered derivative of y, and then we get an n minus k ordered ODE. For this new variable z, this z because this ak is not 0 now, so 0 is not root of the characteristic equation for this new homogeneous equation, new differential operator. Therefore, we can apply the result of case 1 sub case A to this case to solve the z. So z is polynomial. Z is a polynomial of order n. But having obtained z, you integral z k times, you will obtain the y. The integral of z k times will produce the t to the power k for us. Okay, solving this equation, the yk, replace the yk by z, then the derivative of y become lower order derivative of z. Then you can this equation, the new equation for z, can apply the result of case 1 sub case A, and then having obtained z, which is an mth ordered polynomial, you integrate the mth ordered polynomial k times, you will obtain our y. But integrating the polynomial k times, you will introduce k's arbitrary coefficients. But we can simply set the constant to be 0, because we only need to find a particular solution. So we for simplicity, we set the integrating constant to be 0. Then this resulting y will be t to the power k multiply mth ordered polynomial. So this proves the case A sub case B. This proves this result that the solution y is t to the power k multiplied by a polynomial of the same order as b, also the right hand side g, because g is mth ordered, therefore here is also mth ordered. Okay, so this proves the first case, that is gt is a polynomial. There are two subcases. 0 is not eigenvalue, that is the result of our previous theorem, and then 0 is an eigenvalue or root of the characteristic equation of times k. Then we have a tk here. Okay, now the second case is gt is a polynomial multiplied by an exponential function. Here the lambda 0 is a real number, but it might be a root of the characteristic equation or not. If lambda 0 is not a root of the characteristic equation, you consider this as an eigenvalue of times 0. Anyway, the solution is polynomial multiply exponential multiply tk. Here k is the times. Okay, so to prove this case, we introduce our unknown function is y, but we make this transformation. Y is e lambda 0 t x, and then we get an ODE for x of the form. Why the ODE of x will of this form? Our original ODE is for y, but we making this change of transformation. We get an ODE for x. The exponential disappear, right? Our equation, our GT contains an exponential. Our equation is Ly equals GT. So our y is an exponential multiply x. Then all the derivative of y contain an exponential. Therefore, the exponential in Ly will cancel with the exponential in g. Therefore, what remains is polynomial. Okay, so this is the equation for x. That is the right hand side is also an nth ordered differential operator for x, but the coefficient alpha, previous coefficient is a. Now after the transformation, the coefficient might change. Therefore, we denote the coefficient by alpha n minus 1, and so on. And then the right hand side, the g, now because the exponential e lambda 0 t cancels. Therefore, we only have the polynomial. Okay. So we claim that lambda 0 is the root of the characteristic equation of the order k. Then 0 is the root of the characteristic equation for this new differential operator for x. So this is a claim. We'll prove this claim. If lambda 0 is the root of our original characteristic equation, that is the differential operator for y, Ly. If lambda 0 is a root for that of times k, then correspondingly 0 is a root of the characteristic equation for the new differential operator for x, that is which coefficient alpha. This characteristic polynomial we denote by epsilon lambda. The previous is e lambda. Okay, so this is our claim. So with this claim, then our equation for x fall into the category of the case A we just discussed. Then you can apply the result of case A for this equation and get the equation of x. The equation of x is a polynomial of order n, as we proved in case 1. So therefore, the original the solution of the original equation y is exponential multiply x. That is exponential multiplied polynomial of order n. So this is the form of the solution we declare in case 2. Therefore, this proves the case 2. Okay. So to complete the case 2, it suffices to It suffices to prove our claim. Our claim is that lambda 0 is root of e lambda of times k. Then 0 is root of the new characteristic equation polynomial also of times k. Okay. So this is the definition of x. The transformation we introduced before. Then the derivative of y using the Leibniz formula from calculus, the ith order derivative of the multiplication of these two functions is given by this. Okay, so the derivative of this exponential to the I minus j derivative, which is lambda 0 to the power I minus j. Okay, so this is known from calculus. The Leibniz formula, ith order derivative of the multiplication of two functions. Applying the formula, we get this result. Here we compute. We know that the derivative of the exponential e lambda 0 t to I minus j order the derivative give us a lambda 0 I minus j. Okay. Then as before, as in the proof of the theorem, our Ly is sigma I from 0 to n ai y, the ith order derivative of y. So we use the previous computation, substituting the previous computation here. So we can now we have a double sum. The range of the inside sum is j from 0 to I, depending on the summation index of the outside sum. Therefore, we need to use our previous trick to transform the inside sum j from 0 to I to be we have not changed here. We move the exponential out, and the a just move the exponential out, and then we use the trick j from 0 to I, and then I from 0 to n equals I from j to n and j from 0 to n. This is the trick we used in the proof of our theorem 1, where we use the delta ij. Okay, using the delta notation, we can change the range of j here from 0 to I by j from 0 to n, and then switch the order of summation, and then get rid of the delta. Okay, the trick we used before, so we will not repeat it here. So this is the computation. So we go forward. This is exponential lambda 0 t, and then the remaining object is new differential operator for x, applying for x. The arrow here, the new arrow here. So this is the inside sum is the coefficient of the new differential operator arrow x. Okay, so compare this formula. We see that our alpha, our previous alpha, so we make this transformation so that the problem transform into a differential equation, no homogeneous differential equation for x. So the operator is Lx. So compare the coefficient. This Lx is precisely this one. Okay, so compare the coefficient. It follows that the coefficient alpha n minus 1, alpha 1, alpha 0 are precisely given by the ai and the lambda 0, also some other numbers. So this is the relation of the new differential operator, this arrow, and the previous, our original arrow, coefficient of our original arrow, that is ai here. So this is the relation. Okay, using this relation, if lambda 0 is the root of e lambda of times k, that is the case ordered derivative of e lambda and lambda 0 is not 0, and the derivative of order less than k, that is from 0's order, that is e lambda 0 itself, and up to the k minus 1 ordered derivative at lambda 0 are all 0. This is equivalent to the statement that lambda 0 is root of e lambda of times k. Then using this result, this is our alpha j. Our alpha j given here. The alpha j given here are precisely the derivative of the expression of the polynomial. You see, the polynomial is here. You take the jth ordered derivative of the polynomial e lambda, you will get ai and cij and lambda 0 I minus j. Okay, so this is direct computation. So alpha j is actually ej lambda 0. So lambda 0 is root of the original characteristic equation of times t is equivalent to alpha k not 0, because alpha k is this, by this equation. Alpha k is the case ordered derivative of e at lambda 0. Case ordered derivative of the original characteristic polynomial at lambda 0. So ek lambda 0 is not 0, is equivalent to alpha k is not 0, and the other alpha is 0 is equivalent to this derivative is 0. So this proves that lambda 0 is root of the original characteristic equation of times t if and only if 0 is root of the new polynomial, new characteristic polynomial of order k, okay, of times k, sorry. So this proves the result. 0 is root of the new characteristic equation of times k. Okay. Now this proves the second case of our theorem. The second case of our theorem says that if gt is a polynomial multiplied exponential function, then the solution is a polynomial multiplied polynomial of the same ordered and multiplied the same exponential function, but we need to multiply the t to the power k. Here k is the times of the lambda 0 as eigenvalue of the characteristic equation. Okay. So the last case is case 3. Case 3 is gt is polynomial multiply cosine plus polynomial multiply sine and then exponential. This case. For this case, we consider the case that without the sign, because the sign case can be treated similarly. So for simplicity, we only consider this case. Then we set the capital GT to be, we write the e alpha t cosine beta t is the real part of this capital G, right? So using this capital G, so lambda 0 is the corresponding lambda 0 is alpha plus I beta. So this case, this capital G, we consider Ly equal capital G. This is the second case. This is the second case. That is the capital GT is a polynomial multiplied exponential function. Although in our previous proof of the second case, we do not use we don't care whether this lambda 0 is real or complex. Our argument also true even if lambda 0 is a complex number. So now our lambda 0 is a complex number. So the result of the case, we now discuss case 3, but the result of case 2 applies to Ly equals capital GT. Then we apply the result of case 2 to this capital GT equation, Ly equal capital GT. Then obtain the solution, take the real part of the solution, which is the solution of our equation, our original non-homogeneous equation of the form. The form is given here. Okay, so this proved our assertion, that is for GT, for these 3 cases, purely polynomial multiply exponential, and polynomial cosine sine exponential. Okay, so in all these 3 cases, the solution has the form we already know. So this video, this set of video prove this result. Okay.